Yeah, welcome to this presentation session for the ShanghAI Lectures 2013. I'm just going to explain a little bit about what we'll do today. There'll be three presentations: Group 6, Group 9, and then Group 1. Each one will have it'll be about half an hour total. Maybe about 15 minutes presentation plus video and plus questions. So we will start off. I don't know, Fabio, do you want to say any words before we start, or should I just introduce the first group?
I was just saying
welcome, exactly. Yeah.
I want to say welcome, and I want to thank all the groups of all the students who were so daring to take the challenge. So we know it was not so easy. So thank you for trying.
Okay, let's start. Welcome everyone. We are Group 6, and our presentation topic, or our Kōan topic, is that of Braitenberg vehicles. So I'll give you a presentation about the topic. We have an introduction in the beginning with a recap about Braitenberg vehicles and layered control architecture, and present our basic idea. I will present our framework, and we will have a look on some results. So let's start. Braitenberg vehicle is a very simple device, which is basically a coupling between sensors and actuators. It can be of different forms, but it is usually relatively simple. So here you have an example on the right hand side of the slide, where you can see that a device with two. So on the right hand side we see a Braitenberg vehicle, where we see the coupling between two actuators and two sensors, and depending on the coupling of those sensors and actuators, those devices can develop a more complex behavior, such as approaching light or avoiding obstacles or something like that. And our core was to develop something like a Braitenberg vehicle, which has a layered control architecture, which is also called subsumption architecture. And the idea of a subsumption architecture is to have several layers of control, where the most basic layers perform the most basic tasks, and higher layers are responsible for higher tasks. And so the idea is to get a very robust behavior, because if something's not working on the upper layers, you can always fall back to the basic layer, which is usually something like avoid obstacles or whatever you want. And you can implement it in different ways, but usually it is you have several modules which are connected and can inhibit or invoke other modules, and you have somehow in the end a coupling between the sensors and actuators. And because it's embodied AI, we have of course no representation of anything out of our robot, so all we are doing is coupling sensors and actuators. Now, our idea was to build a Braitenberg vehicle which is able to sense colors and paint itself. So our Braitenberg vehicles are supposed to sense the surrounding colors on a field and sense its own color, and can move around on the field and change its own color. But we have also some constraints in the world. So, for instance, we say that it's not possible for a Braitenberg vehicle to drive on a field, on a cell of the field, where the distance of the color to the Braitenberg vehicle's own color is above the threshold. So our framework is relatively simple. We implemented it in Python and used the HSV color space. because it's a cylindrical coordinate representation of color points, and we initialize robots with random coordinates and random colors. Okay, so a word on the color space. We're working, as I said, in the HSV color space. So here you have a representation of such a color space. You can see that hue is around, it's 360 degrees of hue you have here. You have a saturation and you have a value. So it is not, it's not a real, if you measure the distance and we measure the distance in the Euclidean distance in that color space, so that's not really a distance measure like our brain, our eyes would perceive the distance, but it's maybe relatively close, and it's intuitively you can intuitively understand the distances in this color space, because you have, for instance, one distance is to lower the value or to lower the saturation or something. And we have a number of steps where robots can change the color. So each robot is able to change its color in 1% in the hue direction, 5% in the saturation direction, and 5% in the value direction. So this is the maximum change in color which each robot is able to perform in each step. So our color sensor is in this, I mean, we have a field, a matrix, which is a number of cells, and our color sensor is able to sense the surrounding colors in, it's a, yeah, you have a 6x6 field here, and the robot has it has 8 directions, and in all 8 directions, its sensor information is the average over the distances to the colors in this field. So here you see how this would look like. Now our control layer architecture is relatively simple. So we have our sensors on the one hand and the actuators on the other hand. We have 3 layers. The first one is avoid obstacles, which is first to avoid obstacles, as I said, and second to avoid obstacles includes in this case to not drive to fields where the color is too distant from our own color at the moment. Then we have a layer which is does a chase escape behavior in a approximate way, so it can chase colors or it can escape from them. And our top layer is a creative layer. And yeah, I mean, we say, okay, this will be in the creative layer slide. Yeah, and we start over with a list of possible moves and color changes. And in each layer, we reduce our list of possible moves and color changes to select one in the end, which we perform. So, for instance, if you start with a list of possible moves, which is to move to all surrounding cells, in the first layer, we have a avoid obstacle behavior. And if there is a collision in that cell, we remove those moves where the collision is present. So when we move, that's on the one hand a collision with the border of our field, and on the other hand, it's a collision with cells where the color distance is below 10%, above 10%. Okay, the second layer is our escape chase layer. So if we are in escape mode, we select those moves and color changes where the distance is maximum. So we want to escape from our actual color or actual cell. So we choose to go to that cell where the distance is high. And in the chase case, we remove those modes and color changes moves where the distance is maximum. So we remove the same nodes, the same moves and color changes which we selected if we were escape now. And our third layer is a creative layer, but of course it's difficult to say creative. So what we have in the end is randomness. So if we are presented with we have 3 remaining choices for our colors, and we choose a move or a color change at random. That's our creativity. Okay, that's a result. For instance, where we have a 200 and a 100 times 100 field, and started over 200 randomly initialized robots and performed 2,000 steps. And what you can see here is, of course, it's difficult to say what you would expect from such an environment and from such a behavior, but what we can see here is basically some clustering behavior, if you would like to say so. And what's a problem here is in the whole case is that we have often the problem that robots get stuck in some place where they move back and forth, but don't perform global changes anymore. I can give you a short demonstration. I hope I have to see how to do that with a Google Hangout. I change so here is our randomly initialized field of robots, and we can perform those steps and see what's happening. Maybe I start it again and reduce the number of included robots, because it's not so good to see, not so easy to see what's happening there if you have a large number of robots. Now we have 10 robots, and we can see what they're doing. They randomly escape a chaser, and the first steps are usually to reduce the color to the surrounding cells, because at the beginning all cells are white, and we can't move if the distance is too high. So the first step is usually to lower the color values to go down till they are nearly white. And here you can see that one started to move around, and it's presumably an escaper, so it escapes from its own trail. But as there are some, it has always 3 choices. If there's only one trail behind it, and therefore we have our creativity layer sets in, and we have different outcomes. And it's, as you can see, it's you can't see a lot because it's really light image here. But if you would simulate the whole thing more steps, you can see that something like our clustering behavior results, which we showed in the slides. Okay, I think we are nearly done. That was our demonstration. I would like to thank you, and do we have any questions? Thanks.
All right, thank you. Thank you very much. Nice presentation, very cool. I like that you do the demo live as well. That's extra pressure. So thank you very, very much. So we will now pass around to some of the TAs that are here. It'll be Nevereth, it'll be me and Fabio, and we will just see what questions we can come up with for you. So Fabio, do you want to start off? Or do you want me to start off?
I want to finish.
What do you think? Yeah.
No.
I think we lost your microphone, Fabio. Try again. There you go.
No, I think it's not the idea of Braitenberg icons for painting. I think it's a very nice idea. But so can you tell something about the implementation? So how you designed the Braitenberg icons? By the way, is it in Webbots, right?
No, it's not in Webbots. So because it's, as I said, it's such a simple framework, we choose to
just Python. You told it.
So I can I can send you the code. It's in the end, it's only a matrix of fields, and robots have in each step they can choose to move somewhere, and we visualize it using a Python library.
But how you model the single robot and the Braitenberg icon itself? How you model the connections, the inhibitory and
we have those connections between the layers, and we experimented with different behaviors in the layers, but we don't have this inhibitory or connection, but all we do is we have a list of possible moves and color changes for each move, and through going through our layers, we change those lists until only one move or one color change remains. So we have not really this inhibition thing, but a control layer architecture nonetheless.
No, I see. So I leave. I don't know if other people have other questions, so I can leave the space to have other questions. Maybe.
Okay. Nevereth, do you have any questions?
For now, I don't have. Maybe I can ask later.
I have a couple. So I like the layered architecture you did, especially the Be Creative one. So you said that there's more to randomness than creativity, and I think that's right. And it's kind of a hot research topic as well now in robotics and in neuroscience and in these areas. So that's a kind of a cool thing to include. Now, do you think you could have implemented this in Webbots? Yeah, I think there's I think there's a Python. You can write Python controllers for Webbots. Is that,
I don't know. I mean, I'm sure we could have implemented it in Webbots, but the thing is, as it's really easy to do it directly in Python, we choose to do it in Python.
Yeah.
But if you would really, we say it's a simulation, but it is not. So it's
right.
Because we don't have limited time or anything. We compute the whole stuff and visualize it. So if we would simulate it in Webbots or something, we could definitely do more stuff.
You could do more stuff, yeah, exactly. So it might be more interesting interactions going on. So I think
what we don't have done yet is to have something like a collision detection for robots. So it's possible at the moment that they move together on one field, which is of course not. We shouldn't do that.
Right. And the other question was so where did you get the kind of inspiration for this color change behavior? Is it from a natural example from nature, or how do you come up with it?
It's a thought experiment.
Right.
So I mean, it's a bit like the initial idea was what would be if they could paint and sense colors, could something come out which is visually interesting, but we can come up with an image of the whole procedure. We could say, okay, it is an underwater robot, and it is able to change the height of the ground. So it could it has something like some stuff with it, and it can put them on the ground, so the ground changes, and it can sense its distance to the ground and change the ground, and its own distance.
Okay. Right. Is there any more questions from Nevreth or Fabio?
Maybe I can ask one question. Actually, I'm curious about in the simulation. So, for example, for the sensor case, like how did you simulate that? The field of like sensor vision. The range.
In that case, it's simply the sensor is gets the color values from the surrounding fields, average over them, and that's all. So our distance measure is a Euclidean distance measure. So we have distance measures to 3 fields, and we average over them to have a distance measure for the field.
So based on the hue table, you have you created some values for the colors, right?
Yeah, colors are represented as a tuple, with a hue saturation value.
Okay.
And
so you simplify the situation in a matrix model.
Yeah, it's really easy. And exactly, you have a 3-dimensional space, and you can use a Euclidean distance to compute the distance in the space. So if you would really simulate it really good, you could of course think of sensor ranges and stuff like that, but that's not in our simple implementation. We didn't do that.
Okay, thanks.
Okay. Any more questions?
Yes. 2 questions that maybe we can do to everybody. The first one is that are you available? If you are available to open source the codes, everything?
Yeah.
And maybe also to publish this on YouTube. I don't know.
Yeah, good idea.
If you agree, now we need your agreement. So I think you should not be ashamed of your presentation. And the other one is how did you interact in the group? Was it a good experience? So you had which kind of problems you had and which kind of things you appreciated? So the first question is practical: are you okay with publishing everything?
Yeah,
and
of course.
Is how was the experience in terms of distant cooperation?
To the first question, I posted a link to our GitHub repository in the chat, so you can have a look at the code. To the second question, it's always a bit difficult to cooperate over continents, but I think we got everything working, so I'm glad for the experience.
So you are roughly, so the difficulties are, which kind of difficulties you met?
It's everything worked, but it's like yeah, you could wish for a. I mean, if you compare it to group cooperation and a local group cooperation, you can sit together and discuss everything. And we didn't do something like a hangout or something where you could do that really, but we discussed it on ShanghAILectures.com, which is okay. But of course, if you don't have the direct communication as in a hangout, there's something which is.
So you didn't try to use Hangout during the project, during the before. I mean, did you try to use Hangouts while we work?
No.
Because probably.
But maybe as one could. I mean, it would be a good thing to use Hangout or something like this.
Yeah, or similar systems.
Yeah. And if I can give I think what would be great for future Shanghai lectures to have something like an evaluation between the dates of the presentation and everything else. So you could
to have an intermediate
stages exactly. So yeah, the first stage is to present your idea. Second stage is to present your progress, and the last one is to present.
This is a good suggestion.
Yeah,
okay. So thank you again, because you did a great work, and actually you are part of an experiment. So thank you.
Thanks.
Excellent. Yeah, I agree. Thank you.
Yeah.